Precalc, outline 4.3. Today we're going to talk about trig functions on the unit circle. So we're going to do a little bit of groundwork first. We're not going to talk about the unit circle until the very end. So basically, once we introduce this idea of the unit circle, I'll demonstrate a little bit on how we are going to build the unit circle. But then what we'll do tomorrow is we'll finish anything up that we have here. And then after that, we'll start getting into having us create our own unit circles and start to have a little test on putting one together from memory and being able to build it, just so that just in case you ever need to use one, you guys will know how to build it, where it comes from, things like that. So the first up is the trig functions of any angle. The biggest thing here is just that you're realizing that you have this nice little drawing that you can make at any given point, and that the connection between all of these things. So if you let theta be any angle in standard position, remember standard position would be at the vertex at 0, 0. Positive x-axis is where you start your rotation. Up is going positive, down goes negative. It says that the point P, x comma y, be a point on the terminal side of theta. Let r represent the non-zero distance from P to the origin. It says that r is equal to the square root of x squared plus y squared. It can never equal 0. Now, we're not technically on the unit circle. The unit circle always has r equal 1. In this case, it's not always going to be true. But what it says is that there's a connection between this triangle that you're going to be able to make here. Anytime I do a rotation of theta, there's going to be this triangle that I can create, and this triangle has sides here, with this being y and that being x, and the hypotenuse of that triangle is r. And it's just using Pythagoras Theorem because it does form a right triangle. And the cool thing about it is that you can then, if you wanted to memorize, which I feel is kind of ridiculous, we already know SOHCAHTOA. And if you know SOHCAHTOA, you know the big three. Once you know the big three, you take the reciprocals to find the little three. So you don't have to remember these ratios the way they are. But what they're going to do, and later on we're going to figure this out, talking about reference angles, is that theta can represent the angle at the origin. So that's really theta. And so when I say sine of theta, sine is opposite over hypotenuse. So you notice that opposite of theta is y, hypotenuse is r. So that's why you get y over r. Cosine is adjacent over hypotenuse, so that's why it's x over r. Okay, and tangent is opposite over adjacent, so it's y over x. Notice that x cannot equal 0. If x equals 0, then you're dividing by 0. That means that that ratio does not work. The little three are just the reciprocals, cosecant, secant, and cotangent. Just take the reciprocal of each of those relations. So basically what I'm trying to get at is that if they said that you or told you that you have a point that lies on a terminal side of an angle that is in standard position, you have an xy, like in part A down there in our example, is that 4, 3 is on a circle or on some angle. It's the terminal point. It stops there. You are actually able to find the values of all 6 trig functions by drawing yourself a nice little diagram. So this is what I say that you should do. Roughly graph that. So if I graph this, if I go 1, 2, 3, 4, 1, 2, 3, you know your point someplace about there, yeah? And the cool thing about this is that if I draw a triangle from the point to the origin and then straight down to the x-axis, it forms a right triangle. The right triangle is the important part, and it's always the origin to your point straight to the x-axis. X-axis, not the other one. And then what I want you guys to do is put your values in. How far to the right did I go? How far to the right? I went 4. 4 to the right, which is a positive 4, yes? Then I went 3 up, which is again positive. I now have x and I have y. I need to know r. To find r, they gave us the clue above, use Pythagoras Theorem, basic. And so, r is equal to the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16. 9 plus 16 is 25. Square root of 25 is 5. So, that means the hypotenuse is 5. I left something off. I forgot to say something. We left the fact that I need to put theta inside at the origin, that origin angle. That's theta. So now, I just want you to list sine, cosine, tangent of theta. You don't know what theta is. I could care less what theta is. Now, you guys, according to, is it 4.1, I think, we could find theta. Take the inverse tangent, inverse sine, inverse cosine. But, right now, all I want you to do is say, we'll do sine first. Sine theta equals cosine theta equals tangent theta equals. And those are the big three, using SOHCAHTOA. If you don't remember what SOHCAHTOA is, write it down. SOHCAHTOA. Make sure to write that down on your paper. That way you guys never have to forget it. It's always going to be there. But sine is what? Opposite over hypotenuse. Okay. That's 3 over 5. Cosine? Adjacent over hypotenuse, which is 4 over 5. And tangent would be 3 over 4. So it's not too bad, right? That's the big three. And once all 6, so now you have to do the little 3. The cool thing about this is I'm just going to take sine's ratio and I'm going to take the reciprocal. And that is cosecant theta, which would be 5 over 3. I'm going to take the secant theta, and that will be 5 over 4. And cotangent theta is equal to 4 over 3. And you've now just found all 6. Okay. Notice that this was in the first quadrant, yes? X and Y were both positive. The next problem, I have negatives. Again, you still graph it like normal. You just know you're going to go backwards and down. That means your X and your Y are both negative. The hint on this one, before I let you guys try this one on your own, is that R, your radius of your circle, your hypotenuse of your triangle, is always going to be positive. Always, always, always think of that when you're using Pythagoras Theorem. Square a negative, it is positive. And if you square root a positive, it's a positive. Okay, so try part B on your own. Alright, so you guys, as you guys are working, 1, 2, down 1. There's my point in space. I'm going to connect it to the origin, connect it to the x-axis. It's 90 degrees. So it's a little bit tougher on here because the marker is filling it in. The theta's at the origin angle. I know that I went backwards 2, so it's negative 2. I went down 1, so that's negative 1. And then all I have to do is negative 2 squared, which is 4 plus negative 1 squared is 1. Square root that. Square root of 5. That's a really bad square root of 5 in there. Let me see if I can make that better. Square root of 5. A little hard to read on the screen, but the radius is square root of 5. So now when I do sine theta, cosine theta, tangent theta, I now have all of the sides. Sine of theta is -1 over square root of 5. Now you can fix that. I possibly would fix it, as in it should be the negative square root of 5 over 5, because I multiplied bottom and top by square root of 5. Cosine would be -2 over the square root of 5. And tangent would be -1 over -2, which actually turns into 1/2. Cosecant theta equals negative square root of 5. Secant theta is equal to negative square root of 5 over 2. And cotangent theta is equal to 2. So it's not too bad when you are given a point that says that it's on the terminal side of an angle in standard position. Make a triangle, make your little diagram, connect it to the origin, put your theta in there, and then find it. Now again, I could ask you at any point now, find theta. Well, I could take the inverse sine of -1 over square root of 5. The inverse cosine of -2 over square root of 5. The inverse tangent of 1/2. You will get the same theta every single time. At least you should. Make sure your calculator is in degrees if you want degrees. It's in radians if you want radians. I'm not going to ask you that in this problem. Are we good? So, the next easiest, or I think the easiest angles to actually understand are what we call the quadrantal angles. Now they're calling these the common quadrantal angles, bless you, because we're not talking about going around the circle many, many times. It's the first 4 quadrantal angles. The first one being the fact that you go 0 degrees. And if I go 0 degrees, guys, it's going to be r comma 0. So whatever the radius is of your circle, that's what it is. It's how far out. So if the radius is 4, it'd be 4 comma 0. If I go to 90 degrees, or pi over 2, we should start to remember some of these. So 90 degrees, pi over 2, I am going to go straight up. 0r. Now if I'm on the unit circle, which we're going to get to in a second, that'd be 0, 1. Otherwise, it's 0r. So again, if the radius is 4, I'm going to go up 4. 0, 4. If I'm talking about 180 degrees or pi radians, it's a -r, 0. It's going straight left. Again, on the unit circle, it's -1 comma 0. And the last one is 270 or 3 pi over 2. It's straight down. So it'd be a 0 comma -r is where your quadrantal is. So, it says that it wants you to find the exact value of each trig function if defined. If not defined, write undefined. Now, one thing it doesn't do here is that it doesn't give you an x or a y. It doesn't tell you the radius of your circle. And so we're going to have to assume that we are on the unit circle, which has a radius of 1. So you guys all know that the unit circle has a radius of 1. So that means r is equal to 1. So it's either going to be 1 comma 0, 0 comma 1, -1 comma 0, or 0 comma -1. But here's the problem. Each one of these that's a cosine, it's a cosecant, cotangent. Well, wait a minute. Cosecant is 1 over sine, so we can change that. Cotangent is a tangent, so it's 1 over tangent. The problem with this is, what is cosine? what is sine? What is tangent? Is it an x value? Is it a y value? They didn't tell us that yet. Well, first of all, where's 270? Let's start off with cosine. 270 would be here, right? So, at this point, you know the terminal point would be what? What would the point be associated with that? Unit circle, radius of 1. So it would be 0, negative 1. Now you have choices. Is it 0? Is it negative 1? Or is it something else? So what is a cosine? Does anybody remember what cosine was? Cosine and sine are the x and y's. Who remembers? We all did this last year, so. Cosine is the x value. Put this on your calculator, guys. Make sure you're in degrees. Make sure you're in the right mode. Do cosine of 270. You should get 0. It should equal 0. It's the x position. So I'm going to add that on here real quick. I think it's actually on the next slide. But your points, guys, are all made up of cosine theta, comma, sine theta. So your x's are cosine, the y's are sine. So, hence, we got to 0, negative 1. The x value is 0 because I'm not moving left or right. I'm just going straight down. Did everybody get 0 when they put in cosine of 270? I hope so. What about the next one? Cosecant of pi over 2. Well, first of all, where's pi over 2? It's 90 degrees, straight up. So, that's the second photo up there. So it should be 0, comma 1, right? Okay. Wait a minute, cosecant, that's not one of my cosine, comma, sine. So therefore, I got to switch this to the big 3. What is cosecant again? Cosecant of pi over 2 is equal to 1 over sine of pi over 2. Ooh. So wait a minute. That's easy enough. What's the sine of pi over 2? Still the same photo up here, same drawing, but it's the y value. So it's not the 0, but it's the 1. And so this becomes 1 over 1, which is 1. I'm just replacing the value or the trig function of sine of pi over 2 with its value of 1. And then 1 divided by 1 is 1. Cotangent, I don't like cotangent either. So what should I replace cotangent with? With tangent, but it's not tangent, it's 1 over the tangent of negative 90 degrees. Wait, where's negative 90? It's going backwards, it's going down, right? So therefore, actually, I would have to be here. Negative 90. So that gives me that point again of 0, negative 1. But wait a minute, tangent, that's not, again, one of my cosine, comma, sines. What is tangent? This was something we did on, I think, one of the first days. We started talking that cosecant was 1 over sine, secant is 1 over cosine. What was tangent? What was cotangent? There was ways to switch this thing to sines and cosines. Tangent is sine over cosine. So you're saying is that this is 1 over the sine of negative 90 over the cosine negative 90? Would that be okay? because tangent itself is sine of theta over cosine theta. But it's in the basement, so I have to leave it like this. But wait a minute, when you divide by a fraction, you flip and multiply. So it really should become cosine of negative 90 over sine negative 90. And wait a minute, cosine, sine, I can do that. What's the cosine at negative 90? AKA x value. Over negative 1. And 0 divided by anything? 0. And you're done. Okay. So let's move on here to make our lives a lot easier. Because not everything is between 0 and 360 or 0 to 2 pi. And so we need to use this thing we call reference angle. Now the book will distinguish between theta and its reference by using a comma or apostrophe after it. So this is like theta of an apostrophe after it. So one's theta, the angle that you were given, and the other one is what we're going to call our reference angle. And the cool thing about it is reference angles can be used to find trig values of any angle theta. Why? Because the value of sine theta will be the same thing as sine of the reference angle theta. They have the same value. It's because everything's linked back to the same values. Think about the unit circle. Well, we haven't got to the unit circle. Think of a circle. If I think of like looking at those little diagrams that they have there, even just taking a look at this one right here, it's got more of the circle here. My y value goes up, 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 up to the top, and then back down. It's going to pass the same x and y values on the way up and then on the way down. And so therefore, there's only so many values. And so that value is going to come up again and again and again and again. The sign's going to change, if you guys remember that. But everything can be used as a reference. Hence, we did those reference triangles. Because those reference triangles are going to be very helpful for us. Now, to find reference angles, there are different rules for different quadrants. Remember, there are 4 quadrants. 1, 2, 3, 4. Following that counter clockwise rotation. So, if you're in the first quadrant, theta is its own reference. You don't need to use reference angles. If I'm in quadrant 2, though, the reference angle is always the angle that gets you back to the x-axis, the shortest distance to the x-axis. So therefore, this red angle is the reference angle. And to find that, all I would do is take 180 minus the angle theta. Or if I was in radians, be pi minus theta. So if I have a 150 degree angle, its reference angle is 30. If I have 2 pi over 3, pi over 3 is my reference. If I'm in the third quadrant, which is down here, theta is the red. So now I am past 180. So the quickest way back is to take the angle theta and subtract 180. Not take 180 from it, or not take it from 180, but this time actually subtract 180 or subtract pi. If I'm in the fourth quadrant, I will go all the way to the circle, so it's 360 minus theta, or 2 pi minus theta. That will give me the leftover. How much would it take to finish the angle off? Okay. So the last thing I want to do for today is I want to find those reference angles. It wants you to sketch it first, because maybe by sketching it you might be able to see where you're at. You'll be able to tell which quadrant you're in. The first one is 5 pi over 4. So, remember, when you go 5 pi over 4, you're cutting pi into how many pieces? 4. 1, 2, 3, 4. 1, 2, 3, 4. So there should be 8 total pieces, yes? Can you count 5 in the positive direction? 1, 2, 3, 4, 5. There you are. Now, I'm in radians. I'm going to give my answer in radians. Don't convert these to degrees. Essentially, what would it take to get you to go back to the x-axis? How many pi's over 4 did you overstep? 1 pi over 4. So guess what? Your reference angle is pi over 4. Reference angles are going to always be positive. Positive, positive, positive. So theta, reference angle of theta is pi over 4. What about part B, a negative 240 degrees? That means I'm going to go backwards, right? How far is this? Negative 90. How far is that? 180. How far is that? That's too far, isn't it? So I can't go that far. So I have to be somewhere about here. I don't know really. I'm just guessing. So my angle would be there. The coolest thing about it is that you now know you're in which quadrant? You're in the second quadrant. And if I went back to 40, what would it take to walk back this distance? How far would I have to go? Now these rules, actually, that kind of changes my rules just a little bit. The rules actually reversed because I went backwards. But the reference angle is always going to be positive. So basically, ignore the negative. It's 240. And 240 what? What do? Minus 180. And 240 minus 180 leaves me with an angle of 60 degrees. So therefore, theta prime, or reference angle, is 60 degrees. So it's slightly different than what we had up above. We took 180 from it. We didn't take it from 180. 390. Wait a minute. 390, that's bigger than what? 360. So I go all the way around. How much further? 30 degrees. Wait a minute. Wait. We went further than 360 by 30 degrees. So what's the reference? 30 degrees. You guys getting the hang of this? You guys seeing how it's just the leftover getting us back to the x-axis. 14 pi over 3. Pi's are cutting into how many pieces? 3. So 1, 2, 3. 1, 2, 3. I am not counting the 90 and 270. Do you see that? That's why I changed colors. How many of them am I moving? 14 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I ended right there. How many more would it take to get me there? One more step, and each step was worth how much? A pi over 3. Boom. You just found your reference angles. Page 253 is your homework, day 1, 1 through 23 odds. Have a great day.